Hi guys, here is that trig review as promised. And the purpose of this is just to, make sure that we don't lose any more points unnecessarily because we forgot trig. And when I was thinking about this video, I purposely did not prepare notes for myself because I just kind of want to go off the cuff and just recall everything, like the basics of what I would expect to know from trig, just purely bringing it off of memory. And, I haven't taught trig for a while and I haven't taken trig for a while. So these are kind of things like that you just are expected to remember for the rest of your life. Okay, so I mean maybe that's not true because I'm kind of a person who uses math a lot. But like in general, these are kind of things that it's just like the same way that you never forget the Pythagorean theorem. I'm gonna keep it at the same sort of level of things that I would expect us to always remember. Okay. So let's think of a quick outline. What are the things that you should know? First of all, sine and cosine functions, and by extension, other trig functions. At multiples of pi over 6. Multiples of pi over 6. Or if you want to think in terms of degrees, multiples of 30 degrees. And of multiples of pi over 4, or if you're thinking in degrees, that's 45 degrees. Okay, you also want to know, what else do you want to know? Basic identities, and in particular relating the 6 trig functions. Okay, you also want to know SOHCAHTOA. Well, if you don't know what that is, then we'll recall it. But I kind of feel like that's one of those things that you never forget to. SOHCAHTOA, and also just a couple other identities. A couple extra identities. And then this is like, when I say a couple, really only the ones I think about are sine squared plus cosine squared. And then maybe we'll throw in 2 sine. That one's sort of iffy, honestly, because I only remember that one recently. Okay, and then also graphs. You should be able to graph any of the 6 trig functions. Yeah, and I think with just that covers like the majority of trig to me. If you know all those things, then you kind of know, you have working knowledge of what you need for calculus. Okay, so let's start with the sine and cosine, and by extension, let me highlight here. So sine and cosine, and by extension, the other trig functions at multiples of pi over 6 or pi over 4. And the way to think about that is in terms of the unit circle. And so here's a fact to remember. Okay, fact: cosine represents x value, and sine represents y value. When I say that, I'm talking about on the unit circle. Okay, so let's draw the unit circle. Another thing, I didn't specify explicitly, but yeah, the unit circle is for sure one of those things that you want to have a grasp of. Okay, that line was way off. Try to draw that through the center as close as possible. Okay, something like that. All right, so let's start with, we said we want to know values of pi over 6, right? And we want to know x and y values, or cosine and sine values. Let's start with the first interval. So the way I view the circle, the unit circle, I view it as a circle that you can traverse by multiples of pi over 6 or by pi over 4. Let's do pi over 6 first. So start from 0, right? And then you have 1, 2, 3 pi over 6. 3 pi over 6 covers one quadrant. For each quadrant, it's split into 3, right? 4, 5, 6. 7, 8, 9, 10, 11, and then 12. So at 12, you're back to where you started, which is 2 pi. A full circle is 2 pi. That's another fact we should remember. 2 pi is a full circle. And so pi is a half circle, right? And each of these are pi over 6s. And the way I think about this, since I'm going by pi over 6s, I just count. So 1 pi over 6, 2 pi over 6. I know this is unusual to write, but I think of this as, in one sense, 3 pi over 6. And this is 4 pi over 6, 5 pi over 6, and 6 pi over 6 is 1 pi, right? 7 pi over 6, 8 pi over 6. This is 9 pi over 6. 10 pi over 6, 11 pi over 6. And this can also be thought of as 2 pi over 6. I'm sorry, 12 pi over 6, Okay, so if you want any of the sine or cosine at any of those values, then you can just count how many are you around to find the position you're at. And then now once you know where you're at, let's talk about how you do those calculations. So let's just pick a random one. I'm gonna pick 4 pi over 6. Okay, so let's redo this circle. 4 pi over 6 right over here, right? Actually, let's keep the same circle and just kind of work with this guy. So 4 pi over 6 right there. Now, if I look at 4 pi over 6, what's really happening here? Let's clean up everything else. Okay, no, it's just to get the distractions out of the way. I'm going to zoom it. I'm going to focus in on 4 pi over 6 as an example. So anytime that you do one of these multiples of pi over 6, what you're really looking at is you're looking at this triangle right here. You're looking at this triangle right here. And this triangle is a very special triangle. It's called a 30, 60, 90 triangle because this small angle is 30 degrees. The bigger angle is 60 degrees. And then you have the right angle right here. So you have a 30, 60, 90 triangle. Let's extract that triangle. Just pull it out bigger in this side. Okay, that was very inaccurate. Let's try that a little bit nicer. Hopefully. Okay, still pretty inaccurate, but you have to get the picture. Okay, so this is the right angle here. This is the bigger side, 60 degrees and 30 degrees. And remember 30, 60, 90. 30 degrees is just another way of saying pi over 6. And 6 degrees is another way of saying 2 pi over 6 or pi over 3 if you prefer to reduce. Okay, and then 90 degrees you can think of as pi over 2 if you don't like to work in degrees. Okay, when you have a triangle with those particular degrees, it always has this proportion. This is an amazing fact. The short side is exactly half the length of the hypotenuse. So in our case, if we're looking at the unit circle, this unit circle, the hypotenuse is a radius, right? So the radius is 1 long side. And then short side is always exactly a half. Amazing fact that happens anytime you have this particular arrangement of degrees, 30, 60, and 90. And so the thing that makes this last side work is it's the thing that makes the Pythagorean theorem work, right? We got half squared plus something, I don't know, squared is equal to 1 squared, because that's the long side, short side, right? A squared plus b squared equals c squared. And the thing that's going to make it work is the root 3 over 2. Root 3 over 2. Because when I square a half, I get 1/4, right? So I want this to square to 3/4. And root 3 over 2 is a thing that squares to 3/4. So that makes this medium side root 3 over 2. Okay, all that just to say, anytime you have a 30, 60, 90 situation, you got two possible measurements for your sine and cosine, right? You're going to have either it's a short side where it's a half or it's root 3 over 2. Now that could be positive or negative depending on where you are. But for that, you just think of where you are in the Cartesian system, right? The regular signs. If you're to the right, you're positive for x. If you're to the left, you're negative for x. If you're up, you're positive for y. If you're down, you're negative for y. Okay, so let's come back to 4 pi over 6. What are the two values? We have sine and we have cosine, right? So sine, and we're at 4 pi over 6. So remember, sine is the y value. That's this length right here. This length right here, right? So that's the root 3 over 2. Cosine is the left and right value, the x value. That's the short side, so it's a half. And then now, that's the distance, but you want to know, is it positive or negative? Sine is up and down, so that's positive. Cosine is to the left of the axis, so that's negative. So negative half like that. All right, so now, anytime I have any multiple of pi over 6, I just would think, okay, what triangle am I at? And figure it out from there. Okay, even though I say that, so that applies for this triangle, right? Here's a triangle. Short side is the sine. Longer side is the cosine. Here's another triangle. That's 2 pi over 6 or pi over 3. Short side is the cosine. Long side is the sine. At the next interval, you're right at the straight up and down, right? And straight up and down, this is no longer a triangle situation because you're right at the radius. So if you're at 3 pi over 6, which is just pi over 2, that brings you to one of the straight up and down lines. And so for that one, you just have sine being exactly 1, right? It's 1 to the top. And cosine is left and right, but if you're straight up and down, there's no left and right, so cosine would be 0. Actually, I'm kind of getting talking about two different things right now. Let's focus on other pi over 6 ones. So other pi over 6 intervals, like let's say this triangle, this is 5 pi over 6. Short side is the sine, so sine is a half. Longer side is cosine, so cosine is root 3 over 2, but negative. And the same thing over here, right? Sine is negative half, cosine would be negative root 3 over 2. Same thing over here. This is 1, 2, 3, 4, 5, 6, 7, 8. 8 pi over 6s, or if you prefer, that's 4 pi over 3, if you reduce. Sine is the long side and negative. Cosine is the short side, also negative. And so on and so forth for these other triangles, right? Okay, so the other weird pi over 6, not weird, but the other pi over 6 intervals can bring you to the straight up and down or the straight left and right. But those are easy because if you're straight up and down, then you're right at the radius. That makes the length 1. And if you're looking at left and right, it makes it 0. So for instance, if this is pi over 2, right? Sine of pi over 2 is 1, and cosine of pi over 2 is 0. Same idea here. Cosine of pi would be negative 1, while sine is 0. Okay, so far, we've gone through the entire unit circle. Now we know how to calculate any value of any multiple of pi over 6 for sine and cosine, right? The other thing we said is we should also be able to do pi over 4 instead. So same concept here. The same concept, except we have a different triangle. Same concept, different triangle. So we can traverse this same unit circle. Instead of using multiples of pi over 6, now we're going to take multiples of pi over 4. And a pi over 4 is exactly halfway through a quadrant. So what the heck do I mean by that? Here's a quadrant right here, right? Pi over 4 would be halfway through that. Another pi over 4 brings you to pi over 2. Or if you want to think, this is 2 pi over 4, right? And then 3 pi over 4. 4 pi over 4, which is, of course, just... of course, just pi. That's a terrible 4. Okay, 5 pi over 4. 6 pi over 4, which, of course, is just 3 pi over 2, if you reduce. 7 pi over 4. And 8 pi over 4. Okay, so these guys that go straight up and down, we already know how to deal with them because we already saw them with the... oops, wrong one. We already saw those guys with the pi over 6 route, right? And, those actually are pi over 2s. You can think of them that way. Those are really just multiples of pi over 2, right? So we know how to deal with those already. So I'm going to... Actually, let me just get rid of all these marks for now. Undo all those markings. Okay, so what we're gonna focus on is then the ones in between. So the other multiples of pi over 4. So this is one of them. This is 3 pi over 4 right here, right? I don't know why I made the line go past the mark this time. This will be 5 pi over 4 and 7 pi over 4. And you can always count. If you lose count, you can always go 1, 2, 3, 4, 5 to make sure that you're in the right spot. So that's what I tend to do. Okay, so what do? Let's look at one triangle, for instance. Let's look at the starting triangle this time. Because why not? And remember, sine is up and down, so that's this length. Cosine is left and right, so that's that length. Let's extract that triangle here on the side. Oh, it didn't recognize that as a straight line because it's too bad. Okay, something like that. Oh, that's really ugly, but okay, so we have a right angle here, right? Here, the long side is a radius, and it's a unit circle, so that means the radius is 1. And again, we're using the Pythagorean theorem. We have A and A this time. They're same length because in a 45 degree triangle, those are the same. This is isosceles triangle, right? Or 45 degrees, or if you want to think of it as pi over 4. All right, so now if we just apply the Pythagorean theorem again, what do we have? We got a squared plus a squared is equal to 1. And the thing that's going to make it all work is it's going to be, I want a squared to be a half. So if I want a squared to be a half, then what I want it to be is 1 over root 2. Right, 1 over root 2. So that when I square it, I get a half. So that means a is equal to 1 over root 2, or, like people like to rationalize that, root 2 over 2 if you want to. These are equal because you could multiply top and bottom by root 2, and you get the same thing. So either one. Personally, yeah, let's actually write it as root 2 over 2. Root 2 over 2, those are the lengths. So anytime you have a 45 degree, then that's what the lengths are going to be. This is going to be root 2 over 2, this is root 2 over 2. And over here, sine and cosine both positive. Here, same lengths, right? If you're at 3 pi over 4, sine and cosine would still be root 2 over 2, root 2 over 2, but one of them is going to be negative. Cosine will be negative because it's to the left. Okay, that's it. But whatever it is, so now if I see any multiple of pi over 4, I can just think back to that triangle. Think, okay, I know the sides are going to be root 2 over 2's. And so I know sine and cosine are both going to be that value. Oops. And so this makes it easier to calculate, right? I just know sine is root 2 over 2, cosine is root 2 over 2, and all I have to determine is whether it's positive or negative. There we go. So that makes it pretty simple. Let's do one quick example. Let's change color here. So let's say I want to know sine of 5 pi over 4, cosine of 5 pi over 4. Okay, so I go 1, 2, 3, 4, 5. That means I'm right here. Looking at this triangle, looks like cosine is negative, sine also negative, and their values should both be root 2 over 2. So negative, root 2 over 2. Okay. All right, so now I can calculate sine, cosine for any multiple of pi over 6, any multiple of pi over 4. That includes pi over 2s and multiples of pi as well, because, pi would just be here. That's like 6 pi over 6, for instance, right? Okay, so, and in addition to that, one more quick thing. So coming back to our original plan, if we have the basic trig identities relating the 6 trig functions, right? Basic identities. With those identities, then that means I can also calculate all the other trig functions for those same values. Pi over 6s, pi over 4s, which by taking 2 multiples of pi over 4, you also get the pi over 2s and pi's as well. So that, if you ever see the picture of the unit circle, it has all those values, right? And that's all it comes from. Okay, so let's talk quickly about those basic 6 trig identities, and then we will cut this video off because it's starting to get long. Okay, so what are those? Okay, what are those? Okay, so they are. We have sine, we got cosine. Next one is tangent, which is sine over cosine. Right? Okay, and then what are the ones we have? We have secant, cosecant, and cotangent. Cotangent is just the opposite of the tangent. They kind of actually are paired. They're sort of named that way. Cotangent. It's the co of the tangent. So it's you flip it upside down, right? Cosine over sine. Secant is 1 over cosine. You know, the way I remember this one, this is I don't know if this is really the normal way to remember it, but I think of like this is the co of the secant, and when you look at the letter, the second letter that you see, not the first letter, that's the letter of the starting part of the denominator. So in other words, if you ignore this first letter, you see the S next, that tells you the letter of the bottom here. And just like this one, right? It's not the S to start with, it's the next letter that you see. That's not next consonant that you see, which is a C. And so the cosine goes in the bottom. Okay, that was kind of a weird way to say it. Like, however you remember it, you have to somehow remember these basic identities. Actually, there's only 4 if you think about them, because sine and cosine, everything's written in terms of sine and cosine, right? Okay, so anyways, somehow remember, the way I remember is look for the letter that's not the starting letter, and that tells you the starting letter of your denominator. Right? The next letter is not the starting letter, that tells you the letter of the denominator. For secant and cosecant anyway. And tangent is just sine over cosine. You just gotta remember that. Cotangent is the opposite of the tangent. Okay, so these are basic identities that we need to know. We gotta just memorize those. And then, because that's the definition of them. And then once we have that, then that makes calculating any of them pretty simple, because let's just pick out one at random. Let's say I want to know cosecant of let's see pi over 3. Okay, so if I see pi over 3, I'm going to think back to my circle. What is pi over 3 in terms of pi over 6s? That's 1, 2 pi over 6s. So I have pi over 3, right? Pi over 3 is 2 pi over 6s. I know right here, my cosine is the short side. So that's 1/2. And the sine is the long side. So root 3 over 2. Right? Now, my original problem was cosecant, so I have to think, okay, what was cosecant? Cosecant of pi over 3 is actually, well, that's a terrible 3. 1 over sine of pi over 3. And that means that, I didn't even need my cosine. I just had to remember what sine was. It's root 3 over 2. So it's 1 over something. If I take 1 over something, that just means I'm going to flip it upside down. So it's going to be 2 over root 3. And essentially, that's your answer. Of course, people don't like it like that. They like to rationalize it. Personally, I don't really care too much. But it's not considered simplified. So if you want to rationalize, no big deal. Just multiply by root 3 over 3. And you get 2 root 3 over 3. Right? So there it is. There's your value. And you could do something similar for any of these guys. For tangent, same thing. Just plug in the 2 values, right? For cosecant, same thing. I just did cosecant. I meant for cotangent or secant. Same thing. Right? Just refer back to your original sine cosine values that we talked about how to calculate. Just plug it in for any of the things that you care about. Okay, so the video's getting long enough. Let's cut this off, and then in the next video we'll talk about the remaining ideas.